Okay. Now, there's the quiz problem, okay? So we want to sketch the free body diagram for the block. I didn't say for the block, but I think that's implicit. And everybody interpreted it that way. So here, we have free body diagram. We have the weight. I'm going to express this as negative mgj. There are other ways to do it. You can take your own decisions. We're going to have a normal force. Now, to draw the normal force, we better have the direction of the incline so we can go perpendicular to it. So I do this dotted line in the direction of the incline and then a normal force here. And then there might be a frictional force. Your free body diagram might look like this. Well, when I did negative mgj, that wasn't necessarily the best idea. Because that would assume that your y-axis is straight up and down. You don't want to do that. You can, and go ahead and do it and work it out. You'll understand why it's easier if you put the x-axis parallel to the incline and the y-axis perpendicular to the incline. Because now two of these vectors are parallel to the incline. Okay. Now you got negative mg here. This is the only vector that isn't parallel to one coordinate axis or another. Well, what's that mean? That means I'm going to change my labeling here. Okay, I'm going to call this W. Okay. And magnitude of W is mg. Now, if I write W without an arrow, that means the magnitude of W. I could put absolute value or norm signs around W with an arrow, and it would then mean the magnitude of the vector. But I choose just not to write the arrow. This means the magnitude. Okay, that's how much force, and it's mg. You see that W is acting in an angle with your coordinate axes. If this angle is theta, then you can determine if this angle is also theta. Make sense? So that we can get rid of this vector and replace it by this vector and this vector. Because by the parallelogram method and so forth, if I add these two vectors, I get this vector. It should be very clear. Now, what are these vectors? Okay. This vector is going to be negative W cosine theta times J. Now, that should be obvious if you understand triangles, and I hope you do. If you don't, you really need to bone up on your. This is the adjacent side. This is the angle. That gives you the cosine times hypotenuse. Hypotenuse is your W. Okay, here you've got W sine theta, and it's times your I vector because it's along the x-axis. Well, there you've got all your vectors expressed in terms of their components. Okay, X and Y components, or I and J components. Okay. So now you have F net equals W sine theta times I plus your friction force times I plus your normal force times I minus W cosine theta. And I said I here, it's times J. Obviously, this is in the y direction, so your J vector, okay? And this equals here's your I component. In other words, this is the sum of all the X components. Now, if you want to call this Fxi and Fyj, that's fine. Okay. Yes. Yeah. We have a negative force of friction because we have assumed that the thing is traveling down the incline. So the friction has to act the direction opposite the motion, right? If it was traveling up the incline, then the force of friction would be down the incline, it would have been positive. But I said it was traveling down the incline, so it should have been negative. Everybody understand that? That makes sense? Okay. Okay, so there we have it. Now, do we have any equilibrium here? We might. What would we have to have for this to be an equilibrium situation? Okay, so the question I pose is, could this be an equilibrium situation? What would have to be so for this to be an equilibrium situation? Got a really good answer. Acceleration would have to be zero. Now you make a conclusion from zero acceleration that your net force is zero. Okay. If your net force is zero, that means both components are zero. Now, why is net force zero? Well, because net force is mass times acceleration. If acceleration is zero, your net force is zero. Could the net force be zero? What would it take for the net force to be zero? Okay, so acceleration could be zero, and I guess. Okay, so and I can also say this equals, I should have said the sum of the X forces plus the sum of the Y forces. Either that or write F net X and F net Y. That makes sense? If I just write Fx and Fy, what's that? There's no just plain F in this thing. Every F has a subscript, right? But if I do sum of Fx and sum of Fy, that means I'm just adding up all my X forces here, multiplying by I, my Y forces here. Well, okay. So equilibrium. Acceleration is zero. F net equals m times the acceleration is zero. So F net is 0I plus 0J. So this would then have to be 0. And if this is 0, then these two forces are equal in magnitude, right? And this. Okay, well, if you just pick a coefficient of friction out of your hat and an angle theta, that ain't gonna happen. If they're totally random, because two random numbers can't ever agree that well. Okay. But you could try to adjust the system, as I kind of demonstrated, so that you do get a constant velocity. You can move the ramp until the tendency is for whatever's going down the ramp to slide at constant velocity. That's going to be frustrating because it never works. But you still get an idea that there is an angle at which you'd have a constant velocity. So the velocity, which I just implicitly call V, is constant. Okay, that's the velocity of the block, right? And maybe just make it clear V. Wow. That'll happen for just the right angle. So I'll go further into it. We'll do this more generally. What is the acceleration of the system? What's your expression? What's your expression for the acceleration? How do you get acceleration if you know the net force? That's it. Okay. And in this case, that is this. Now, if you're given enough information, if you're given the mass of the block and the angle of the incline, then you know everything here except what? Okay, so if you know theta and m, W is just mg, so you got W sine theta. You know M, you know what W is, you know what the sine of theta is if you know theta. You don't know what the force of friction is because I didn't tell you anything, but it's going to be mu times the normal force. It's going to be coefficient of friction times the normal force. Okay. You know the normal force. Well, as it turns out, it was given to you, but the J component, let's think about the J component of the acceleration. How much acceleration does this system have in the direction perpendicular to the ramp? Can you show me with your fingers? It's 0. Okay, thing is not accelerating in the y direction. Okay, so now you have equilibrium in the y direction. Such that Fn equals W cosine theta. So when you subtract W cosine theta from Fn, you get M. You get 0. Okay. And I guess maybe I should give you just a little more than that. I'm gonna do my logic a little differently. You have equilibrium in the y direction, since the acceleration in the y direction is 0. Okay. Sum of your y forces is 0. The normal force of W cosine theta. That makes sense? You're not accelerating in the y direction. Okay. So the total net force in the y direction is 0. That means the sum of your y forces has to be 0. You're not accelerating. Y forces have to add up to 0, and here's your y force. Here's the sum of your y forces, right? And the other way this is going to be 0 is if Fn equals W cosine theta. Then your force of friction is mu k times Fn, your normal force. And that's just the principle of friction. Friction comes when you got two surfaces that are pushed together. Okay. So what's happening? Assuming that this incline is strong enough, it doesn't collapse or bend significantly under the weight of the block. The normal force has to be just exactly what it takes to balance the component of the weight in the y direction. Okay? Make sense at all? Okay. You can read about it, but you know, that's what it is. You got something resting on the incline, it's not going down through the incline, it's not coming up off the incline. Moving constant velocity along the incline, then these two forces have to be equal and opposite, assuming there's no other force that's acting in the y direction. Now, what would change if I was pushing this thing horizontally? Then there'd be another vector in there. It's a horizontal vector, my push. Okay, and that push would have a vertical component and a horizontal component. So it would tend to speed the thing up along the ramp, but it would also tend to push the thing up off the ramp. I mean, if I just decide to punch that thing real good, it's gonna come off the ramp, right? Yeah, it wasn't kind of punch I can throw these days, no, but you know, maybe a paper clip. But you know, if you give the thing a strong force in this direction, that's gonna come off the ramp, right? Give it a weak force, it'll stay on the ramp as long as the component of that force in the y direction doesn't exceed this component of the weight. Okay. All right. Well, you see a whole sequence of reasoning here. Now you can reason it out in any order you want, but that kind of summarizes everything you need to know about a block sliding on a plane under the influence only of gravity, normal force, and frictional force. Start adding forces, well, you're going to have problems that ask you to do that, and they just told you what to do with them. Okay? So hopefully that made sense. You can always go back and look at that part of the video. Okay, well, we want to look at other situations, okay, whole variety of situations. So we want to apply the same kind of reasoning 2. Yeah, I'm not one to do this right away, but I think we need to, because it's kind of one of the most important systems you look at, the Atwood machine. Okay? You got the pulley. All this mass M1. All this mass M2. Assume no friction. And we can arbitrarily assume that M2 is greater than M1. Okay? Then what do we know? Well, we know that we got two different masses. We got M1, and we drew this last time, M1G, and we have an upward tension, which I've drawn to be clearly a little bit greater than M1G. Can you see if this is longer than this one? Okay. And then we got M2, where we got M2G, which is bigger than M1G, right? It's clearly bigger. And then we got the tension, which is going to be a little shorter than M2G. Okay, make it about like so. Okay, is it clear then that this thing is going to have a net force upward just from the lengths of the vectors? And this will have a net force downward, right? And this is still T. Yep, we'll leave it that way. Okay. So now, what's the acceleration of this one? What's the acceleration of this one? Okay. Acceleration of this thing is net force I'm going to use I's and J's. Instead of an arrow over the T. So this is T times the J vector. This is T times the J vector. And this will be negative M2G J. This will be negative M1G J. Okay, so now we got T minus M1G times J for the sum of the forces, right? Okay. And we divide by M1. That's the acceleration of the first one. Okay. Acceleration of the second is T minus M2 J over M2. We also noticed A1 and A2 are equal and opposite. One is accelerating upward, the other is accelerating downward. The string's not changing in length, so if this one's moving up at 5 meters per second, that one's got to be moving down at 5 meters per second. Okay? So there it is, set up mathematically. Then all you have to do is set this equal to the negative of this. You know M1, you know M2, you know T, and of course you know G. That's a set of equations you can solve for T. Now, I don't recommend that you memorize this formula for an Atwood machine because we can throw monkey wrenches in the formulas. But understand where that formula comes from so you can always rederive it. Okay? In other words, don't skip the whole process of analyzing your forces and just use this as an equation every time you see an Atwood machine problem. Because what happens there is by the time the final exam comes around, you're going to need to know about 100 equations instead of a dozen principles. Okay? You want to work from principles. Yeah. No, a dozen principles, not 1,000 equations. I'm exaggerating, it's more like 100. Okay, 100 formulas. No, I'm not going to give you 100 formulas. Okay. Principle is tension's the same, and everything follows from that. So you want to think through that. And there's a lot of insight. Now, another insight that you get is there's another way to solve this. Okay, well, actually, you solve for T, and then you can plug that into either of these to find what A1 or A2 is, right? Once you know T, then you can calculate the two accelerations. And you can analyze the motion, and once you know the accelerations and the initial velocities and displacements and all that stuff, then you're just into uniformly accelerated motion. That makes sense? This is how you get to uniformly accelerated motion. Okay, another way to analyze the Atwood machine. Is cal force M1G here, and force M2G here. Okay, what's the direction of motion of this whole system? Give you a hint, it's not up and it's not down because you got something moving up and something else moving down. Yeah, it's rotation. This whole system is trying to rotate around that pulley. Okay, does that make sense? Now, rotation in this direction is positive. Rotation in this direction would be negative. That makes sense? That picture makes sense? I don't want to take time to write out a bunch of words. Okay, so what's the net force in this system? If M1, if M2, well, doesn't really matter which one's bigger in this case. Okay, just take it as they are. So, what force is it that tends to rotate this thing in the positive direction? Does this force tend to rotate it in the positive direction? Is this force? Yeah, if I pull down this way, it's going to rotate in what I said is the positive direction, right? So we can say the net force is M2G minus M1G, because clearly this force will tend to rotate it the other way. And one of the forces is going to win. If M2 is greater than M1, then this whole thing is going to be positive. If otherwise, it'll be negative. And I don't have to make a vector out of this because the motion is just in one direction, either positive rotational or negative rotational. That makes sense? You want to ponder it. Okay, so there it is. So acceleration is F net over M. What's M? The total mass is M1 plus M2. And I factored out the G, but here's G. We just factor out the G since it's common. There's our net force. Again, that's something you can use as a formula to solve the thing without ever analyzing it. Now, on a test, you're going to have to analyze it. Now, if you solve it using that formula, I might give you half credit. Okay. I think I remember using that formula a time or two when I was making a B in my first physics course. Okay. So, my first college physics when I had it in high school. It was a good course. So there it is. That's how you analyze that. Here's one way to analyze it. Here's another way to analyze it. Okay. Clean board here. Here's a pendulum. I use capital L for the length and M for the mass. It's a simple pendulum, so it's actually treated as a point mass. We're going to have mg down. I want to know what the force is here. If I move this back at distance x from equilibrium. That makes sense? Because you pull a pendulum back from equilibrium, it's going to give you more and more resistance. It's going to experience more and more force trying to pull it back to the middle. Seems to have a, forget what it was. It's something really heavy hanging from a hole in the back part, and yeah, you want to pull that thing back, it comes back real easy. You go back a couple of feet and you're fighting it because it's pretty heavy. Okay. So just kind of think about that. You got something heavy and a string that'll hold it, hang it up, feel how the force increases as you try to pull it back. Now, why does that happen? Well, in this situation, I don't have any magnet or anything holding this back. So what do the forces look like? Like for a body diagram, I think most of you drew it, is if we could do negative mgk, and we could do D for the tension. And take off the negative and everything. Put my X and Y axes like this. So I want to know what are the components of MG parallel and perpendicular to T? Relate this. Okay, in terms of X and L and M and G, then if I want to cross out MG, say supply MGY MGX. What's MGY? What's MGX? Well, this triangle here to here to here to here should be congruent to this one, shouldn't it? Okay. That makes sense. So what would MGX be? Well, if you look at this triangle, if the angle theta, which you don't need, incidentally, here's angle theta. Here's angle theta. Theta is between vertical and the direction of the direction of the tension. So again, here's vertical, here's the direction of the tension. That's got to be theta. You would want to say that MGY is MG cosine theta and MGX is MG sine theta, right? Okay, well, can you tell me what the sine of this angle is? What's the definition of the sine? I'm going to try it. Opposite side divided by hypotenuse. Yeah, okay, the hypotenuse, right? What's the opposite side here? Show with your fingers. X. That's opposite theta. What's the hypotenuse? L. All right. MGX is MG times X over L. You don't need the sine. You don't need theta. I never said anything about theta when I drew this, did I? Put theta in there because you probably wanted to see it in order to think about the triangle. But now, this being congruent to this, your hypotenuse is MG, and this side corresponds to this. So your hypotenuse is MG as opposed to L. This side corresponds to X. Okay, just by what's opposite, what's that hypotenuse. So you get MGX over L without ever having to go through the sine. You got all the information you need. And MGY, well, you can work it out. In other words, if this is L and this is X, this is square root of 1 minus X squared, right? And you divide that by L. And it works out. Okay. Now, if this angle is small, in other words, X is much smaller than L. One minus X over L quantity squared is close to 1. Because X over L is small, when you square it, it gets tiny. Okay. X over L is 1/10. Now we only pull this back a tenth. The distance equal to the tenth of the length. X over L squared is 100. And you got 0.99 here, and the square root of 0.99 is 0.995. Very close. There's some approximations we'll talk about later, but you know, I'm still seeing those approximations and trying to grasp the Lagrangian for the general theory of relativity. These approximations occur throughout physics and engineering. But since I haven't been through an engineering curriculum, I can't say how much. All right, but we want to know these approximations. Now, my point is, if this is very close to 1, so that this force here, this component of mg, is pretty close to the tension, which means that the tension is pretty close to mg. If we analyze it as usually analyzed with mg vertical and the tension at okay. Then we can pretty much say, since we can pretty much say that m times the y component in this case of mg is pretty much equal opposite to the tension, because things in equilibrium. It's not moving this way, right? Or this way. It's in equilibrium with respect to this direction, not with respect to this direction. If the tension is pretty close to mg here, it's pretty close to mg here. You're going to say tension is approximately equal to mg. And you break the tension into its two components, Tx and Ty. Ty is approximately equal to mg. Because this is a small angle, because of what I talked about here. Again, we're assuming that x is quite a bit less than L. Okay. Put that assumption in. If x is much less than L, then we can do this. And we can erase our tension. And our Tx is going to equal mg times x over L, same as it did when I had the coordinate system this way, because the coordinate system isn't really tilted very much. You don't have to tilt it much if x is small. Okay, it's a little different than the explanation I usually do. I usually don't go to this picture. But there's hand waving that's involved no matter how you do it. And you think about what I said here, y tension is equal and opposite to a vector that's very close in magnitude to mg. That's why you can make these approximations. The bottom line then is that the net force is approximately equal to what? Putting this picture, what's the net force? Okay, so I asked what's the net force in the vertical direction. Somebody fairly quickly answered, well, it's zero, because to the extent that our assumption of y component equal to mg, okay, it's not quite true, but for small angles, it's close enough that we can use it. Now, what's left? These two forces essentially cancel each other out, and this is all that's left. Now, say in this picture, when x is positive, it'd be negative mgx over L times your I vector. Now, how many of you are taking differential equations? Anybody, have you had differential equations? Okay, so we don't want to talk too much about differential equations, but I'm going to talk about one anyhow. F net is mass times acceleration. Now I'm going to do this and read that MA equals negative mg over L times x. Why negative? Because if x is positive, then the force is in the negative direction. If I'd have drawn this with x negative, the force would have been in the positive direction, right? It's a restoring force. Constant restoring. Well, acceleration is second derivative of position, right? And instead of mg over L, I'm just going to write k. It's just more compact. K standing for compact. Okay. And this tells us that x double prime equals negative k over m times x. Now everybody's had calculus. What function did you study in calculus that has a second derivative that's a multiple of itself? After some discussion, okay, we start with the fact that the net force is mg times x over L times I. When x is in this direction, the net force will be this way. So we can say then the net force is mass times acceleration, and it's going to be mgx over L, but we write that as mg over L times x. We put a negative sign on it because the force is going to be in the direction opposite our displacement x. And we get this result. This is the net force, and that's equal to ma. Well, acceleration is the second derivative of position. We get mx double dot equals negative kx, okay? Which can be arranged that second derivative of x is negative k over m times x. Now it took me about 5 minutes to drag it out of you to find a trigger give it away there, function you study in calculus that has a second derivative that's a negative multiple of itself. First, we try an exponential function, and that doesn't work. You get a positive multiple of itself. But sines and cosines, you get negative multiples. Okay. Then it turns out you can check it out. Just plug this in to this equation. Take the second derivative of this thing on this side. side is going to change. When you take the second derivative, the left-hand side is going to give you negative k over m times x. Okay. Actually, this side is going to change. X is going to be the sine of square root of k over mt. And on this side, you're going to get negative k over m times the same thing. And that's why things oscillate. And it's the most universal motion in the universe. Almost everything is oscillating. I want you to store that away since it comes right out of this model. This is probably the last thing we're going to completely analyze. But if you understand this, then you understand where simple harmonic motion comes from, whether you realize it or not. Okay? That's like the motion of a pendulum, or the motion of this thing that can bring it to rest. Going to start oscillating, it's moving. Move this way, it'll stop and come back this way. We've seen that. Okay. Okay, well, the whole point of this is we're trying to move from free body diagrams to forces and accelerations, right? And that's really what your homework is all about. And good luck with it. Try to get it to me on time. You know, I've only got 2 of them today. Even Monday, I won't have internet until I get to campus. And I won't be able to really review your homework. But after Monday, I should be able to do that, but still get it to me on time. So I can really see where you are and see what you know, see what we need to talk about. If I don't see your work, I don't know what I need to tell you. Okay.